I want to spend the next few minutes trying to motivate the idea of field extensions using this sort of equation of x squared equals 3. So x squared equals 3 doesn't have a solution on, oh, what's happening? Where am I? I jumped to the wrong slide, sorry. Here's where I want to be. X squared equals 3 doesn't have a solution in the multiplication table. There's no number that when you square it, you get 3. I can see 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 4, 4 squared is 1. There's nothing that has the property that you square it and you get to 3. But we could just make one. And this is more or less what happens in regular arithmetic too. Like at some point, you've never heard of square roots or cube roots, and you realize like, oh, wait, I can write down this equation. It's kind of annoying that it doesn't have a solution. And we just sort of invent notation for like, let's say there is some number that is the square root of 3. And we stick it in the field. What do I mean by that? Like we have our multiplication table. Let's just throw an extra element in. And we can start trying to fill out our multiplication table. Of course, root 3 times root 3 is 0. Sorry, root 3 times root 3 is 3. Root 3 times 0 is 0. I can fill in these numbers, I guess. And I might hope that I've now built a field extension. But unfortunately, I don't have a field here. I don't have, if I take 2 elements here and add them together, I'm not in my list yet. So I need to include all of the sort of things that can be built using root 3. I need to include 2 plus the square root of 3, etc. Is there a question? Coming back to this idea of building bigger fields or building extension fields. If I encounter an equation that doesn't have a solution, I can just sort of try to throw it in. But if I want to throw in one element, I need to also kind of deal with the consequences of that choice and throw in all the associated elements that appear. This is technically, I need to take the closure under addition and multiplication. And it turns out that I'm going to end up with 25 elements here. And the extension in more formal notation, I could call this the fields of order 5 adjoin the square root of 3. And this is a sort of formal notation for a field that includes this clock, meaning it includes these 5 numbers, but it also includes a bunch of other stuff that is sort of associated with the square root of 3. So to step back a little bit, we looked at one equation that didn't have a solution. We named the solution, and then we built an extension field using that solution. I could take some other equation that doesn't have a solution and name the solution and build another extension field by including that element. Or I could take some other equation and name the solution and build an extension field in terms of that element. And it turns out that these 3 fields are going to be essentially the same. What do I mean by they're going to be essentially the same? I mean, their multiplication table is going to look like a Sudoku table. And if I rearrange it in terms of a generator, it's going to look like an addition table. So there will be a single generator in each of these groups. And I sort of thinking of it as just like, well, they're all just, it's just the generator and the powers of the generator. I can sort of think of them as equivalent. So that's the sort of rapid download to an introduction to finite fields and the terms generator and root of unity and field extension and how field extensions relate to polynomials. So to really briefly sum up the last hour, prime clocks make fields. If we take some polynomial that doesn't have a solution and throw it in, then we get a field of prime power order rather than of prime order. Fields of the same size are essentially all the same. You don't need to sort of like worry too much about if you know you're looking at a field of order 49, basically the same as all other fields of order 49. And if you write fields in terms of generators, life becomes generally easier. So maybe I hope that a decent amount of this stuck and felt useful, and you maybe feel a little bit more clear context for some of these pieces. Thanks for joining. I am going to stay on for a while, certainly for the next 7 minutes, but probably for a while after that. And maybe we can just sort of shift away from me talking at you and open up for a little bit of Q&A or discussion about what's on people's minds. So feel free to sign off if you feel like not staying for the Q&A, but if you do have things on your mind that you're either wanting to unpack a little bit better or wanting to try to connect the dots about, feel free to jump in.
I have a quick question.
Yeah.
Why would I make an extension field?
That's a really nice question. The answer that I can give in terms of RISC Zero system is kind of not super. Well, I'll say this, I guess. In the context of RISC Zero system, we're using the size of the field as part of our probabilistic test of that everything went right in the receipt generating process. So if I'm using a larger field, then my like denominator of my probabilistic test is larger, and so I get a more effective test by using an extension field. From a like pure mathematics perspective, the idea that I can find a sort of like nested system of related arithmetic worlds is just sort of irresistibly compelling to try to make sense of.
Yeah, I think that makes sense. I guess the thing that led me to wonder, or your answer led me to wonder, is why not just go for the next biggest prime?
Oh,
you know
okay, yeah. I mean, from another perspective, it's pretty annoying that I can't solve all of my equations. So the idea of like when I find an equation that is not solvable, to just add the solution in, and then if I have some other arithmetic in the field that I care about or still want to use, it's mutually compatible. If I shifted to another field, the mapping of like, but what about all of the arithmetic? So maybe there's a situation where for the vast majority of your system, you only need to be using these 5 elements, but for one particular part, you need to be referencing the extension field. If I were to just move to a bigger field altogether, I would lose the sort of ability to map from the small field into the big field. Does that track?
Right. Yeah. Well, I think intuitively that makes sense. I guess I'm not very strong on this math, but that makes sense. Yeah.
Any other comments, questions?
I have one question.
Yeah.
At last point that you were building an extension field, the table wasn't forming a complete field nor multiplicative group. So I am wondering how this can be used as field.
Yeah, let me open my screen share again. You're right that the multiplication table I made there was a sort of naive first attempt. So this, I think, is where you're looking at, right? So I was sort of just trying to motivate from a like discovery perspective. I want to add the square root of 3 to my field, so I could start like this. But this is not a field. You're absolutely right. I would need to include all of these other elements of this form. So if I were to kind of build out the full table, I would end up with a 25 by 25 multiplication table. So this was just kind of like a naive first attempt, and I omitted the like full details of the 25 by 25 table. But you could imagine, like, I have 2 plus 4 root 3 written here. If I write, say, anything from, it's like a plus b root 3, where a and b have to be between 0 and 4.
Okay,
So
I can imagine the whole 25 by 25 table now.
And it turns out that that table will be like fully self-contained. The multiplication, everything will have a reciprocal, multiplication will undo division, and vice versa. So yeah, to build the extension field, we kind of choose one root to add, and then we take the closure under addition and multiplication. Thanks for that question.